All right, so this is Physics 1B for September 28th. Today we're going to continue talking about methods of heat transfer. Last time we talked about conduction, which is a heat transfer that occurs when two things are touching each other. That's probably the one we're most familiar with because we touch things that are hot, like coffee, and we touch things that are cold, like ice. And we have an understanding of, like, you feel some kind of transfer or exchange of heat in that process. Today we're going to talk about convection briefly. We're not going to do any math with that. We're just going to describe it. And then we're going to talk about radiation. And then we're going to move into discussing, like, specifically gases. And that's going to be the rest of the class. You'll see on here some things that you may have heard before. The ideal gas equation is something you're probably all somewhat familiar with. Maybe you've seen PV diagrams in your chemistry class. I don't know. Pressure volume diagrams. And then we're going to go into, I don't think we'll have time for this last part, but we'll get there eventually. We'll talk about, like, where the ideal gas equation comes from using physics. So we want to kind of create a model of how molecules in a gas work. And we want to have an understanding of, like, how does the ideal gas equation and the variables involved relate to things you learned about in physics. Specifically, what we want to derive is how is temperature generated from kinetic energy, basically. We want to look at the connection between temperature and kinetic energy. So that's the goal for today. I don't think we'll get through all this stuff, but we'll do what we can. So let's talk about convection first. So the first thing I would say is, do any of you know what convection is? What is convection? It's a type of heat transfer. When have you all heard the word convection? Never? Ever? Convectional ovens, yeah. Okay, what's a convectional oven? What's unique about a convection oven versus a non-convection oven? Yep, that's probably correct. What else? What about the sound when you're running a convection oven versus a normal oven? There's a fan. That's pretty much right. Yeah, that's pretty much right. So convection is basically like heat transfer through mass motion. So the convection oven works off the idea that if you can get the air inside the oven moving around, you can make it so that let me zoom out just a little bit and move some of these things around. You can make it so that food heats more evenly, like you said. So I just pulled this out of the book because we don't have, like, mathematics to talk about convection, but we do know some things about convection. Okay. So we're going to we've done this before, we're going to keep doing this because there's a lot, like Physics 1B, there's a lot more descriptive things and a little bit less math sometimes. So we're going to read this together. It's a pretty short paragraph here. So this is a picture of, it says a heating element in the tip of this submerged tube. So there's some tube that's submerged in a fluid, warms the surrounding water, producing a complex pattern of free convection. So this flow of kind of heat you're seeing here is really a flow of mass, wherein the hot mass at the bottom is kind of moving to the top. Convection's related to the idea that, like, hot air rises, like the air in your home. It works off the idea that if you heat air near the ground, that hot air will tend to rise up in the room and create what are called convection currents. We'll talk a little bit about that in a second. Okay, so convection is the transfer of heat by mass motion of a fluid from one region of space to another. That's pretty much the idea. Familiar examples include hot air and hot water home heating systems. So what's meant by that? So the idea of that is, like, if you have a home, so we'll make this really simple. You've got one room, let's say, and you want to heat this room. So when we heat our homes, it's usually due to some type of heating element. It may be a vent, it may be a furnace, something like this, but you have some place where heat is produced, right? That heat warms up the air in the room. So the air down here gets warmed up, and then that warm air tends to kind of rise up in the home, right? And so you get this flow of warm air flowing up like this. That warm air is going to displace any colder air that was in the top. It's going to cause the cold air to fall down. So you get this pattern wherein you have cold air going this way, you have hot air going the other way, and it creates basically a current. So it's like you get this repetitive process. The hot air comes up, the cold air comes down, it gets heated by the furnace, so it becomes the hot air goes up, and so you get what's called a convection current. You get this flow of heat in the home, and it makes it so that even if you just heat the air at the bottom, you get kind of an even heating throughout the home due to convection, just moving the air molecules around. Right? Okay, so it says if the fluid is circulated by a blower or a pump, the process is called forced convection. If the flow is caused by differences in density due to thermal expansion, such as hot air rising, which would be this right here, the process is called free convection. So in the oven that we were talking about, that would be forced convection, because there's like a blower that's forcing the air to flow in some kind of pattern. Then they talk about some other things here. Free convection, the atmosphere plays a role in the daily weather. Convection in the oceans is an important global heat transfer mechanism, because you can have hot water and cold water transferring heat. On a smaller scale, soaring hawks and glider pilots make use of thermal updrafts to warm the earth. The most important heat mechanism for heat transfer within the body needed to maintain nearly constant temperature in various environments is forced convection of blood, with the heart as the pump. So we have this convection that's occurring in our bodies that forces that keeps our bodies uniquely, evenly warm. So then it gets into how this process is complex and there's no equation to describe it, which is kind of good because it means you don't need to memorize any equations for this. But here's some facts about it. The heat current due to convection is directly proportional to the surface area. That's why radiators and cooling fins, which use convection to transfer heat, have large surface areas. So radiators, what's a radiator? Radiator would be like those things that you often find in older homes that are used to heat things. They're like these tubes that kind of wrap around on each other. When I say radiator, is that like, does that mean something to y'all? Do you guys know what a radiator is, or what it looks like? Okay. So they're designed to have like a lot of surface area. Cooling fins with this, for me, I think about like inside of a PC. One of the ways in which you cool a PC is you have these big, large pieces of metal that are designed to basically like transfer heat out of the system as quickly as possible. And the bigger they are in terms of surface area, the better. So they can be very wide and thin. They talk about how viscosity affects it. And then some things about heat current due to convection is found to be approximately proportional to 5/4 the power difference, the 5/4 the power of the temperature difference between the surface and the main body of the fluid. I don't know what that's supposed to mean. All you need to know about convection in terms of this course, and maybe for as you go on, is just that it's heat transfer by motion of mass, by moving mass around, whether that be due to a pump or whether it be due to naturally how hot air rises and stuff like that. Okay, so that's convection. Do you have any questions about that? That's about all I'm going to say about that, so we can get on to some more useful things. So the next thing we want to talk about then is the last method of heat transfer, which is called radiation. So I'm going to put over here what I typed up about it at least. So radiation, and here's some equations to do. Let's push them off to the side for now. Radiation is the transfer of heat via EM waves. And what's EM? Here, let me make this a little bit bigger here. So radiation is the transfer of heat via EM waves, which can be visible light, infrared, or UV. I probably shouldn't just use EM. The word EM means, maybe some of you already know what it means. EM stands for, what does it stand for? Yeah, that's right. So this stands for electromagnetic. So the transfer of heat via electromagnetic waves, that can be visible light, infrared, UV. Literally all bodies, the sun, the earth, you, your car, emit this type of heat. Heat from the sun is delivered across the vacuum via radiation. So radiation is very different from conduction and convection in the sense that it does not require physical contact. In the case of conduction, if you want to feel the heat from a pot of coffee, you've got to at least touch it or at least get your hand close to it so you can feel the air around it and how it's warmed. Same thing with convection. You have to feel a massive heat move towards you. With radiation, there's heat being emitted by all objects. One evidence of this is you can have something called like infrared goggles that allow you to see. So IR stands for infrared. Infrared means light that is just out of the visible range. That type of infrared radiation, you can use like infrared lenses and infrared goggles to view. You guys have probably, yeah, it's like kind of like night vision. It's not, it could be, it's one form of night vision. So let me pull up a picture of this. It would be, yeah, for sure. So this would be an example of a picture generated by like infrared light. Where what you're seeing here, go ahead. I think there's some types of animals that can see some portion of the infrared spectrum, yeah. So here's night vision. This is maybe what you're thinking about with night vision, the kind of green vision. But here's another example. We have at the school an infrared camera. It almost looks exactly like this, and you can turn all the lights in a room off, and you can point it at the room. And when we do this demonstration in class, what you see is all the students show up kind of like this. You see, like, there's a temperature scale here, right? So the hotter the object is, that's what the color represents here. So you can see that the person's hands, as well as the person's face, are hotter than their clothing, right? The clothing is a little bit cooler because we emit energy. The clothing doesn't, but the fact that the clothing is in contact with the person makes it so that, it's going to be kind of warm. It's not going to be cold. But everything else in whatever room this is in is just dark because it's cold, basically. How cold? Well, it's not freezing cold. It's just colder than the surroundings. The scale here goes from 95 to about 70 degrees or so. So this energy is given off, and it's a form of heat. Like I said, it's given off by the sun as well. And that's what we call radiation. It's energy that's given off by electromagnetic waves. So what is this? Well, you kind of need to take a whole class to understand what this word even means. But the idea is that when you have there's a phenomenon called electricity that you guys are somewhat familiar with. The idea that positive charges exist inside of like atoms and stuff. Two positive charges repel each other. A positive and negative charge attract each other. That's something you probably know a little bit about, the electricity part. You're probably more familiar with magnetism, though, in reality, because you have magnets that you stick on your fridge. You probably played with magnets at some form as a kid, whether with toys or whether you just pick some magnets and play with them, right? You learn things like, certain types of magnets can repel each other, other types of magnets can attract each other. In the middle of the 19th century, so in the 1860s, it became very clear to scientists that these two things were not different from each other, but they relied on each other. So one of the things they figured out is that you can produce a magnet with electricity. It's called an electromagnet. So that's kind of the root of this word right here. This is something you probably all know about, because the idea is that if you take a piece of wire and you wrap it around a nail and you pass electric current through the nail by attaching it to, you pass electric current through the wire by attaching it to a battery. What happens to the nail if you do that? By just describing that, was that enough to tell you what I mean? The idea is you take a nail, right? Ideally something that's made of like iron. Iron is really good at this. You take a wire, You wrap the wire in kind of this circular pattern like this around it. And then you take your wire and you connect it up to really any kind of a battery. So if you have a battery right here and you connect it up like this, what happens to the metal right here? Delvino says it gives it a magnetic field. It just turns it into a magnet, basically, right? It allows you to... Sorry, this is something you guys are somewhat familiar with, right? No? It's just always seemed like when I was a kid, I'd go to a science fair and there'd be like 6 or 7 people that did this exact same thing for their science fair project. Yeah, fiddle with those in elementary school. Exactly, Delvino. That's what I'm talking about. Yeah. So by doing this, by having a battery, passing electricity around the nail, you can take something that was previously not a magnet, and all of a sudden it can do things like it can pick up little paper clips and stuff, right? So that's shows us, to some extent, the connection between electricity and magnetism. The other really crazy feature, and this one is much less normal to experience, is that just by moving a magnet near a wire, you can produce electricity. Isn't also the same theory for rail guns? Yeah, you can produce a type of gun out of this called a rail gun. Yeah, that involves basically the same kind of interaction. Another strange phenomenon is that if you move a magnet near a coil of wire, it will actually produce electricity, and that is at the core of how we generate all power in the world, is by moving magnets near wires. The most common form of this that you may have heard of before is like hydroelectric power. What's hydroelectric power? It's where you take falling water, right, and you use that falling water to turn some type of a turbine, which is just a fancy word for a water wheel. And then the motion of that turbine, when you connect the turbine to a magnet and put the magnet inside of some coils, generates power, generates electricity. All right? So all these things that I'm describing, the nail that turns into a magnet, the motion of a magnet in a coil to produce electricity, I think it would be reasonable to ask, what the hell does that have to do with heat, right? Because we're talking about heat. So what do all these things that I'm talking about have to do with heat? And the simplest answer is you need to go take a class in E&M, but that's not a very acceptable answer, right? So what I thought we would do is, this is for something different here. But what I thought we would do is there is a FET simulation that I think does a really, really good job of describing how this works. This is it right here. So hopefully this will actually play. All right, so what's an electromagnetic wave? So this is a particle. It's a positively charged particle, okay? And what I'm going to tell you, just as a preface to this, is the only thing you need to know to understand electromagnetic waves is that when a charged particle accelerates, it emits waves, okay? What kind of waves does it emit? Well, we haven't talked about waves yet in this class, so let's talk about those for just a second. A wave is something as simple as a ripple in a pond, yeah? If you got a nice still pond and you throw a rock into it, there are waves that are going to emanate out from the rock, right? Those are water waves. And most waves that we understand require some kind of a medium. In the case of a water wave, it's water. In the case of a guitar string, if you pluck a guitar string, there's a little wave that oscillates back and forth on the string itself, and that wave will generate sounds, right? Both the wave on the string and the sound that you hear, those are both waves. Like the sound that you hear comes from a sound wave, which is a pressure wave through the air. So water waves, waves on strings, sound waves, they all require mediums. Water waves require water. Sound waves require air, right? You can't talk to people in the vacuum of space, right? Not without like a radio headset or something. And waves on strings require the string, right? So what's an electromagnetic wave? So an electromagnetic wave occurs in a very similar way, except that the thing that you disturb is kind of ephemeral. It's kind of like non-existent. I'll give you an example. So the lines that are drawn right here, moving away from this little positive particle right here, some of you probably know what they represent. Does anyone want to say what they represent? So those of you that have either taken 1C or in 1C right now. What do these lines represent right here? They're field lines, exactly. Now, those field lines are completely imaginary to some extent. But if we take this positive charge right here, and I moved it just a little bit, and you see a pulse go out, like right there, right? If I move them at all, you see those little waves that are going out? I'm doing it very gently here, but we can do it erratically. You see how like a wave goes out? That's a wave. A wave doesn't have to be like up and down and up and down and up and down. It can just be a pulse that goes out on like on a string. Think about, the way you should think about this is, imagine you take like a long extension cord or a hose, some type of heavy cord, right? And you take that cord and you whip it, right? You do exactly, so imagine that this long line right here is a cord and you just like, you whip it like this. You've seen like this kind of thing happen before, right? Where you whip something and a little pulse goes out on it, right? That's something, I hope you guys are all familiar with that idea, right? Yeah. Okay. Well, this is no different, except the thing that is being kind of whipped is this field. And the waves that come out just like that, okay? Now, I'm going to cause this thing to, we can do things like I can bump it. We can make it move in different ways, but I'm going to make it move in a very simple pattern that you're all kind of familiar with, a sinusoidal pattern like this. So now what we have is a positively charged particle, and that particle is just oscillating up and down, right? Because it's going up and then down and then up and then down, it is accelerating. Would you guys agree with that statement? It's definitely accelerating. How do I know it's accelerating? How can I tell that it's accelerating? Acceleration is key, by the way. You need to have acceleration to produce these waves. How do I know that this particle is accelerating? I'm not trying to be too tricky or anything like here. This is some physics 1A stuff, if you can remember. The waves, no. No. Barron's right. Rouge is right. It's changing directions. That's it. The waves are, yeah, these are produced because it's accelerating, but the fact that it changes direction, the fact that it's going up and then down and then up and then down means that at one point in time its acceleration is up. At one point in time its acceleration is downwards. It's definitely accelerating. Its velocity is changing. That's all that really matters, is that its velocity is changing, right? That's all you need for acceleration. That fact produces the waves, and it's that simple. Anything that's charged, that oscillates, will produce these kind of waves. And that's an electromagnetic wave. That's what it is right there. That's what you're looking at. It's a little more complicated than this because these waves, they're three-dimensional. They're not two-dimensional. There's another oscillation that's occurring that you can't see right here that would be into the page and out of the page. And that oscillation is produced by a magnetic field at right angles to what you're seeing right here. Okay. Now, how that all works, you don't need to worry too much about it, except to understand that we call these things electromagnetic waves. That's all you need to understand for this class. And they're produced by accelerating particles. So let's, there's other things we can do with this, right? You can do the circular one too. That one looks kind of cool. Mostly just ends up looking kind of trippy. But it's definitely a good simulation because this is, yeah, okay. So we're going to stop this for now. So radiation, which is what we're talking about again, is the transfer of heat via those waves that we just saw, okay? And literally all bodies emit this. How do I know all bodies emit this? Well, if you take any object, okay, any object at all, let's say, for example, we take a pot of boiling water, for example, or something like this. And I think about, so let's say that this water is subjected to heat from the bottom, so it's being heated up. And now what I want to do is I want to think about an individual water molecule inside of here. So you've got your oxygen, you've got your hydrogens, we got our little water molecule in here that looks like Mickey Mouse. That molecule is composed of charges, right? In addition, this molecule is never sitting still. It is always going to be bouncing around and oscillating, maybe oscillating this way, maybe oscillating this way, you know. Those oscillations will emit electromagnetic waves in all directions. Some of those waves may be absorbed by some of the material or something like this, but literally any object that's hot is going to emit waves, and that's where these pictures come from. These pictures are generated because molecules in the person's face are oscillating, right? They're vibrating, and there's trillions and trillions of molecules inside this person's face that are oscillating to produce this picture right here. The molecules inside the person's shirt are also oscillating, but they're not as hot, right? So they don't produce the same, level of radiation. And then you take it to a higher level, and you've got like the sun. The sun is literally a gas of charged particles. That's what it is, right? The sun is basically just a gas. Well, it's not really a gas. It's a plasma, right? It's a superheated gas that's basically full of hydrogen ions that are positive and electrons that are negative, and every single one of them is just oscillating like crazy, right? They're all jiggling. When I say oscillate, I mean they're just jiggling around, right? They're just sitting there and they're vibrating as fast as they can, bumping into other things, right? But it's literally just, it's a gas of charged particles, and the fact that it's a bunch of charged particles means that it can produce a whole bunch of electromagnetic radiation, and that electromagnetic radiation has the effect of, if this is the sun, and then the Earth is right here, those waves that are coming from the sun are how we heat the Earth up. The electromagnetic waves that come from the sun, they can pass straight through the vacuum of space, really without losing that much energy. And yeah, they can make their way here to Earth, and they're the reason why we have life on this planet. The energy that's used to power the planet, the energy that is contained within fossil fuels, all of it at some point or another came from the sun and from these electromagnetic waves that are produced and that can pass through space. Without these, if there was no such thing as radiation, the Earth would be cold, because space is empty, largely empty. There's some small density of matter in space, but it's an unimaginably empty area, right? That's what we call it, space. But yeah, so that's what electromagnetic waves are. That's what radiation is. All right, what do you guys think about this? Do you have any questions? Yeah. So what I would say is that it is a bunch of things, but the simplest answer I can give you is that all particles are always doing this. They never stop moving, They never stop moving. They're like little kids with tons of energy. They're always moving. That's part of it. Motion of electrons between shells can emit energy, and let me actually, I have a simpler answer to your question, Baron. It's the fact that they're hot. It's the fact that their temperature is not zero. Does that make sense? Anything with temperature is going to jiggle. It's gonna vibrate, and that's what causes these motions like this right here. In addition to interactions with other particles, right? Like, you can imagine that sometimes these electrons get close enough to the hydrogen ions, and that causes their path to get deflected around them, which would cause acceleration, and that acceleration would also produce electromagnetic waves, right? Yeah, did that answer your question, Baron? Okay, good. Ruja says, if all particles are always moving, why doesn't everything go off heat? It does. Everything does give off heat, Ruja. It does. Yep. And how do you know? Well, you could get a type of goggles, right? So you can actually see the heat that's coming off of it. So maybe what you're thinking, Ruja, is like sometimes you don't feel the heat from certain objects. Is that what you mean? You're really only going to feel heat if you touch something that's hotter than you or colder than you. If you touch something that's about the same temperature, you're not going to feel it. In addition, the amount of energy delivered by radiation that we're talking about may be very, very small, and you might not be able to feel it, right? So if you placed your hand, let's say, a couple inches above a table, and the table is 70 degrees Celsius and your skin is like 90 degrees Celsius or whatever it is, There's probably technically, these waves of heat, these electromagnetic waves that are being generated from the table. You're just not really going to feel it, because it's not, it's not very intense. Whereas the intensity of the radiation from the sun, you can feel that in a way, right? On a really hot day. Now, whether you're feeling just hot air molecules hitting your body or whether you're actually feeling the intensity of the radiation from the sun, I don't know. What do you all think? You can certainly, like, when the sun is glaring down on you, right? Let's say 3 in the afternoon when it's just really hot outside on a summer day or something like that. Do you think you're feeling this radiation from the sun, or are you just feeling the hot air around you? Does that question make sense? Do you think you feel the radiation, or do you just feel the conductive air around you hitting you? Can you think? Sure. Yeah, that's the question I'm asking. I don't honestly know the answer. Barrett says that's why my parents told me to wear sunscreen. Yeah, exactly. The warmest type of radiation is visible light. I don't. That may or may not be true. I don't know. That's something we could maybe go read about. I would think that like the warmest radiation would come from like, the higher energy stuff, but I could be wrong. It seems to me like what Barron says. You think you feel the radiation, like you. There's a big difference between, like you're saying, how hot the air feels when the sun's like directly on you versus how hot the air feels when the sun's not directly on you. Whether that's all radiation, I really don't know though. We're gonna do some problems here. Maybe those problems will kind of address these issues. Um, so, uh, oh, what happened here? Yeah, what's up? If you're moving with it. Let's see. So you're moving like up and down just like it is. So relative to the particle, you're not moving. I think you'd still no. I think you'd still observe it. Yeah, I think you'd still have physical observables that you could use to determine that it was there. Yeah, that's a good question though. Maybe I'm oversimplifying, but I think you would still be able to see it. So this is our model for radiation here. A couple equations. We'll do a couple problems too. So again, I pulled this out because there's a lot to this equation. So heat current. Remember that heat current is dq dt, I believe, right? This is the symbol we used before was dq dt, the rate at which the heat is transferring. If you're taking physics 1c, this looks an awful lot like electric current, where electric current, the Q is something different, it's charge, but regardless, heat current is the rate at which the heat comes in, right? That's heat, the energy transferred. Okay, so it says the rate of energy radiation from a surface is proportional to the area A. Okay, so that's going to show up in our equation, area A, to the fourth power of the absolute temperature, T. Why is it the fourth power? I don't know, you got to take maybe some more physics to learn where that comes from. Or maybe this is just an empirical result. The rate also depends on the nature of the surface, okay, which we describe this dependence by a quantity little e, which is called emissivity. It tells you, how much can it emit radiation. It's a dimensionless number between 0 and 1, so this is just kind of a ratio, effectively. It's the ratio of the rate of radiation from a particular surface to the rate of radiation from an equal area of an ideal radiating surface at the same temperature. I believe an ideal radiating surface at the same temperature or more specifically, an ideal radiating surface, has a name, actually. Does anyone know what that name is? An ideal radiating surface with an emissivity of 1. Anyone ever heard of what that might be? If you know what it is, Ruja's typing. A superconductor is something that can conduct electricity with no loss of energy, no internal resistance. But I believe that the name we have for a ideal radiating surface is a black body. Have you heard that before? Or have you heard the term black body radiation, maybe? Something like coal. Have you never heard that before? Okay. This is definitely something you'll hear about more in detail. In this class, we'll talk about black bodies. But it's something like coal that, like, if you think about like hot coals in a fire. Okay. So emissivity also depends somewhat on temperature. So we can express the heat current, dq dt. I didn't realize it was written there. Due to radiation from a surface as. So here's the heat current. It's equal to A, the area, times the emissivity. And then you've got the Stefan Boltzmann constant, which is just, it's just effectively like it's like a conversion factor. It's a number, it's a constant. You can see what the units are right here. And then multiplied by temperature to the 4th power. The temperature is absolute temperature. So it has to be, you have to put the temperature in Kelvin here because you're raising it to the 4th power, right? So you'd have a lot of issues with raising. Think about this. Suppose I have an object that's at 40 degrees Celsius. I have another object that's at negative 40 degrees Celsius. Certainly the hotter object is going to be emitting more heat, right? But if we didn't put it into Kelvin, they'd both have the same answer because to the 4th power means you get rid of the negative sign, right? So that doesn't make any sense. So you have to put it into Kelvin temperature. But there you go. We're not going to derive this. I don't know if this is derived somewhere. My guess is this is more of an empirical result. Although I have a feeling that Planck may have actually, I think maybe he actually derived something like this later on by using little oscillators, but maybe I'm wrong. There you go. That's heat transfer via radiation, via these EM waves that sometimes we can see them with visible light, sometimes we can't. Let's do a problem. Do you guys have any questions? We'll do 2 problems. One where you just have one object, and then we'll do one where you have 2 objects. Let's see if I can put these both on the same page together. You can at least see that right there. Okay, these problems they're very, very straightforward. You shouldn't have too much problem with these kind of things. So we have a thin square steel plate. So we've got a plate. It's 10 centimeters on each side. 10 cm by 10 cm. It's heated in a blacksmith's forge to 800 degrees Celsius. We're given that the emissivity is 0.6. See, this is basically just a fraction that tells you it's like 60%. So 60% of the radiation is going to come out of this thing. If the emissivity is 0.6, what is the total rate of energy radiation from the plate? Okay, so this object, it's emitting heat. We know what its temperature is. Its temperature is 800 degrees, but we need to add to that, 273? So its actual temperature is going to be 1073 Kelvin. And we literally just plug the numbers into this equation. The rate of heat transfer from this object is going to be 0.6 times the area of the plate. So the area of the plate is going to be 0.1 meters times 0.1 meters, so we can just square it. And then sigma, which is this big long number here. Stefan Boltzmann constant. This guy's name, Boltzmann, you're going to see that show up quite a bit as we discuss like physics 1B stuff, because he was one of the people that figured out a lot of how this field, we'll say thermodynamics or what's called statistical mechanics, came about. So it's watts divided by meters squared. I always hate the way they write these. Like, I know that this is in the denominator, but the way they wrote it doesn't look like this is in the denominator, but whatever. Being kind of nitpicky, I guess. So that thing multiplied by t to the fourth, so did I do this right? 1073. I'm sure you guys will say something if it's wrong. So what's that equal to if you calculate that? Notice that this constant's really tiny, right? It's times 10 to the negative 8, but you're multiplying by something to the fourth power. And the something you're multiplying is probably in the order of 100 to 1,000. So I would think that this is going to kind of squelch out this 10 to the negative 8 number a little bit. So I get 451. Does that sound right? I guess you guys are writing it down too. Good. So 451. And the units for this would be what? What are the units for this going to be? Can you see it within the units here? You've got Kelvin to the fourth, meters squared, watts. Yeah, joules per second. Energy per second. You could compare this to like a light bulb. I think, but no, personally, when I think of watts, I'm always thinking about light bulbs. This is like 4.5 times as much energy as might be emitted by 100-watt light bulb, you know. Any questions? It's just a lot of like just kind of just trust this works kind of stuff going on here. All right. So what happens whenever you have a substance that's emitting radiation and another substance that's surrounding it and absorbing that radiation? Okay, that's the next question. And for that, it's really pretty simple. This is our equation, and we'll do this problem that's right here as well. So if I have two objects, okay, and I have one object that's hotter than the other one, or one object that's surrounded by something else, then we simply have a net heat current, where the net heat current is going to be the same formula, and then we just subtract away the absolute temperature of the surface versus the absolute temperature of the surroundings. Okay, and a positive value means a net flow of heat out of the body. This happens if T is greater than Ts, but of course, if you have, let's say, an ice cube that's surrounded by air, or something like that, then the surroundings would heat up the object. But it has to be radiation, so let's see how that works out with this problem here. Zoom out. I think we're gonna run into some problems that I didn't really quite shift these things over as much as I should have. So just give me a second. That should create enough room. All right. So this is what we want to do, and here's a problem to kind of look at the application so we can understand what this even means. What is the total rate of radiation of energy from a human body with a surface area of 1.2 meters squared? Is that a good number for 1 meter squared? That's pretty big. I guess that could be the surface area of a human. A surface temperature of 30 degrees Celsius, which is this, if the surroundings are at a temperature of 20 degrees Celsius. What is the net rate of radiative heat loss from the body? And it says the emissivity of a human body is very close to unity, regardless of your skin pigmentation. So our bodies are almost like what's called a black body, a perfect radiator. So, yeah, I mean, this is a bunch of numbers here, right? So we're going to get net heat is equal to our area, 1.2 meters squared. You multiply by emissivity. In this case, we're saying the emissivity is 1. Hey, did I put the 0.6 in the last one? I did. Okay, just make sure. Sigma which was something like 5.67 times 10 to the negative 8. And the unit was watts divided by meters squared, and then divided by Kelvin to the 4th power. I love it when it does that. And then we need to multiply this by, so we got sigma to the temperature difference to the 4th power. So the hotter object, I believe, is the body, so that's 303 Kelvin. And then the colder object is 20 degrees Celsius. So we add 273 to that, so we get 293. And this will give us the net loss due to radiation. By the way, this is only radiation. And I would assume there's also some conduction that occurs too, but yeah, so what's that equal to? Plug a bunch of numbers in, much like a lot of the formulas in this class. Oh, no. That's not right. That's not right. What's wrong with the equation I just wrote down? Can anyone notice what it is? Exactly. So this should have just been 1.2 meters squared, and then we do that. All right. So I get 72 watts. Okay, pretty easy, right? Yeah. All right, so you'll have some problems related to this kind of stuff on your next homework, but it shouldn't trip you up too much. And that is it for, I think that was chapter 17, talking about methods of heat transfer. So we talked about conduction, convection, radiation. We also talked about, within the same chapter, the way in which when you heat an object up, it can expand. And that was pretty much it for that chapter, I believe, along with just the idea of, calorimetry too. A bunch of calorimetry stuff. So there we have it. What we'll do next, we'll take a break, but we'll come back and we'll talk about just gases, basically, for the rest of class. Ideal gas equation, and hopefully eventually we get to the connection between temperature and kinetic energy. All right, so let's take a break until 11:10.